If you're curious about home automation but don't wanna deal with Home Assistant, then a Quap switch is a perfect project for you. I made two boards and decided to show both of them later in the video. First one I built way back in the past, and it doesn't use a microcontroller or anything. I decided to make new one using an 80Tiny85, which has much more sensitivity and some protections against false triggering. So today we're gonna be building this. I started putting randomly components into the breadboard until actually something works, and I decided to go with the 80Tiny85 as the microcontroller to basically switch the LEDs I'm putting here, and then after that I will make a schematic out of it. So here I'm ready for the first test, and as you can see it works like it should be. All the LEDs are lighting up. I was quite happy with the result from the prototype on the breadboard, so I decided I will just remove everything from here, design a schematic out of it, and then solder them on a perf board and connect them to the mains and to some lights to see if they will actually work. And the circuit is pretty straightforward. There's the mic and an op-amp which amplifies the signal, and the gain is adjustable with this 10K potentiometer here, so you can set the sensitivity of it. Now I added two capacitors, so it will amplify more the high frequencies, so it's basically a high pass filter. And then the signal goes into this 80Tiny85, which controls two LEDs and the output relay. And there's also a 5V supply for the whole thing. I started soldering the IC sockets first, and it was also with this thin solder. Then I choose a supply for the circuit. This is a really cheap one from AliExpress. It was really easy to find, and I basically get the cheapest one, 5V supply, which can deliver, I don't know, a few hundred milliamps probably, but it's just enough for the case here, because it will power just that one relay. Came out pretty, isn't it? And now it's time for the first test. And I just powered it up, and this strange program occurred that it's catching some noise and it's blinking quite crazy. So I hooked up the scope at the output from the op-amp to see the waveform, and I was getting these kind of strange spikes kinda randomly occurring all the time. So I thought the problem is in the power supply, because that's the power supply rail and there's quite a lot of noise there. And I decided to add a decoupling capacitor, tantalum 1 microfarad I think, and that indeed reduced the noise. And here, of course it didn't work. So I realized I actually hooked up this capacitor the wrong way. I connected it straight to the ground instead of the divider, and probably from the ground we're getting some noise, some grounding loop, I don't know. So I quickly changed that and tried it again, and actually this time we have a success. It's working like it should be, but I seem to replace the LEDs the wrong way, but that's not a big problem. And now it was time for the first bigger test with the white bulb. I was hoping for the best this time, and indeed it happened. It just works amazingly, and it's quite sensitive, and it doesn't trigger on a false quap or anything. So I made this simple code, and basically I constantly measure from the analog input pin the value from the output of the op-amp and compare it with these two preset trigger values, and then this code is also compatible with Arduino if you don't have an 8-tie. Here both switches running, and I'm kinda impressed how well the old one is handling compared to the newer one which I just built. So let's see what we have in the previous version. So I actually didn't have a schematic and I had to reverse engineer it. It's not the simplest one you could find on YouTube, but it's very reliable compared to its components. This time for the power supply I use a capacitive dropper together with a bridge rectifier and a 12V Zener diode to stabilize the voltage. And since there's a stray path for the mains to come through the output, you should never touch any part of the circuit while it's running. Then there's a 5V regulator to supply the op-amps and ACs, and the 12V goes only to the relay. The first op-amp amplifies the signal from the microphone, and here we have a diode and a capacitor. Together they form a rectifier. They rectify the voltage from the microphone, and then there's this 100k resistor which can discharge this capacitor, so the voltage here will drop really fast when there's no sound coming in. And then this voltage is compared with the second part of the op-amp, which is used as a comparator. It's comparing it to a set DC voltage from this 100k and this 10k resistor. If the voltage here is higher, then it will output a pulse which will go into the next IC, and all that this IC does is to toggle its output pins 2 and 3 depending on the pulse. If you have a pulse on the input, it will switch, for example, let's say from the second pin to the third, and if it receives another pulse, it will switch from the third pin to the second, and it basically toggles the output and switches the relay. Now I think here there are a few improvements that can be done. First one is, in the first circuit I used a high pass filter to filter out the low frequencies, so I think this capacitor should be changed to around 10 nanofarad, and this resistor to 33k, that will form a high pass filter which will block the low frequencies from coming in. Next, I think the feedback should be going from here after the diode and not before the diode. This way we will eliminate the voltage drop of this diode, so the op-amp will stabilize this voltage here instead of this voltage here. So here it will output higher voltage to basically bypass the drop of the diode, and so this should theoretically increase the sensitivity of it. And now I think this capacitor should be much higher value, let's say 470 nano, so it will have a longer time to discharge here, and that should increase the stability. Let's make these changes and see how it's gonna work. I had hard time replacing those capacitors here, and the result is, I think there's a bit of improvement, but not that much. Here actually I'm running both the boards, and as you can see, you can separately control both of them, because one triggers with 2 clocks and the other one with just 1 clock, and then you can use both boards to trigger, for example, 2 different lights in the same room. I want to note that both of these PCBs are old, and the footage of this video was recorded almost 3 years ago, and in these years I made a lot of projects, so I will show them and stay tuned for that.